Okay, good evening, or sorry, afternoon, or morning for some of us. Um, so, what is the pointer? The middle? Oh, I see. Okay. All right. So today I'm going to talk about a multimodal approach to try to link structural and functional properties of white matter. Um, I'm sure all of you know white matter is the connecting tissue of the brain. It's made of axons that are shielded by myelin. And myelin basically tissue that is covering the axons, so the crosstalk between axons don't happen. So the action potentials are transmitted in a way that are kind of intact throughout their path. Uh, this myelin is basically maintained by glial cells, and glial cells need glucose metabolism to establish this or maintain myelination. So, in a way, I want to say that more myelination would be really is a more metabolically costly process. Um, but that aside, why we study white matter? It's not like we ran out of brain structures to look at, but white matter essentially shows changes in cerebral metabolic rate of glucose, but also blood oxygenation level in correspondence with tasks. So when you stimulate the brain, you see changes in the white matter in that sense too. However, for example, bold changes in white matter has been recognized to be controversial because some argue that bold signal is more sensitive to postsynaptic synaptic activity that is pretty much predominantly seen in the gray matter. But that didn't stop us from looking into white matter, for example, from an ICA point of view. So here you see a single subject data that highlights a network within white matter that pretty much has a very rhythmic pattern of activity with a confined peak in low oscillatory regions that we also recognize to be important for resting state activity, particularly below zero point 0.1 hertz. This is also supported by anatomy. We know that white matter structures have their own distinct vasculature support, and seeing this network pattern may be related to that aspect as well. Well, that aside, we talked about myelination, we talked about glucose metabolism, and we talked about BOLT. But what are some of reasonable predictions or hypotheses that we can make from this data? One is maybe if there's more myelination in the brain across individuals or less, then that might translate into efficiency of brain networks, and maybe we'll be able to see differences in whole brain glucose metabolism and metabolism in the white matter, as the level of myelination is different between individuals. And again, as I noted earlier, more myelination would be also maybe related to more metabolic supply within individuals. Another aspect is if these fluctuations in the white matter are not just noise and not locally confined, but are related to aspects of resting state fluctuations, then we should be able to see some association between the level at which white matter is related to the rest of the brain and its metabolism. Here I'm presenting data on two cohorts. Basically, we had 2 resting state sessions per subject. We also had resting state cerebral metabolic rate of glucose that's measured with PET-FDG. The subjects were divided into 2 cohorts, a discovery cohort and a replication cohort. The discovery cohort, pretty much we had the conventional fMRI sequence with larger voxels and a TR of 1.5 seconds. In the replication cohort, we used basically the connectome sequence, so it was faster, basically sampling, and voxels were smaller. And T1 and T2 weighted sequences were also different between the 2 cohorts. For myelination, we used the T1 to T2 ratio as an approximation for myelination, as other speakers also pointed out. And deep white matter structures were identified with FreeSurfer, and we also quantified cerebral metabolic rate of glucose for white matter with the proper parameters for white matter. Okay, for characterizing functional connectivity in the lab, we use this technique called functional connectivity density, which in a way can give you a proxy for local and global functional connectivity in a way that the properties are the same type. So we're basically talking about voxel count, but the global measure is just overall how many voxels are connected to the given seed or given voxel, and the local is just the size of the local cluster. As opposed to the overall number. These two measures are highly correlated, so I basically here look at the distal functional connectivity by dividing the two measures, global over local, and taking a log transform. Here you could see the map for the white matter on the top row for the discovery and the bottom row for the replication cohort. I just highlighted the underlay for all these images is the actual, for example, measure that is being discussed, but the color part is just color coded, so then you can see the distinction and the basically gradient for that part. One problem is with white matter measures, if the structures are nearby, for example, subcortical areas that are really high in metabolism, then there is a big deal of partial voluming. And basically, we always correct for partial voluming in a way that we would correct for effect of white matter in the gray matter, but now we want to do the opposite, so I think we still need to work a little bit on the methodology there. But what I did here was to basically try to chop the data or remove segments that are really high values in terms of glucose metabolism to basically get rid of all those yellow areas that you see here. For myelination, again, you could see the map. There are some similarities, but quite surprisingly, there are also differences between the two. And I think I blame that for them having different coils and sequences. But it's also kind of alarming because a lot of us use this ratio, so it doesn't seem to be quite consistent. For local functional connectivity, it looks rather similar between the two cohorts, and it highlights certain areas in the white matter. And for the measure of distal, you also could see there's a good agreement between the two cohorts for areas that show high or low distal connectivity within the white matter. For the results, across subjects, basically, if you take the average glucose metabolism in the white matter and average myelination within white matter, there was an inverse association. So the more myelination, the less metabolism. So that one interpretation could be that it is supporting more myelination, supporting more efficiency and maybe less metabolism in the brain. For the association between glucose metabolism and remote connections, we also observe a negative correlation in both cohorts. Again, average metabolism within white matter and within the an average remote connectivity within the white matter. The direction is a little bit, I think, controversial to interpret, but maybe if those fluctuations in the white matter that are linked to the remote areas of the brain is a good thing, then maybe that is leading to more efficiency and then less metabolism. But that, again, I think we need more evidence to really support that. Within individuals, you can also look into how cross-voxels, these measures are correlated. So in both cohorts, as I originally brought up, higher metabolism was linked to higher myelination within individuals. So basically, we saw a positive correlation in both cohorts for that measure. For association between metabolism and remote connectivity, this was not reliable. So we saw a stronger correlation in one cohort, but in the other cohort, this wasn't really reproducible. And that could be maybe this phenomenon is not true, or it could be because of sensitivity of the sequences that are different. So it would have been nice to have the same sequence, but two cohorts, but we learned also from this approach as well. So in summary, there was association between and within individuals, again, with myelination and brain glucose metabolism, and apparently that could be linked to a concept of efficiency in the brain with the way myelination is related to metabolism. But we also saw that the measure of metabolism in white matter was linked to the extent to which fluctuations in the white matter are linked to remote areas in the brain. So this maybe gives us a clue that fluctuations in white matter may not be all just noise, and we maybe should be rethinking that concept. Again, there are limitations for this work. I didn't really correct for effect of partial voluming, the effect of how sensitivity of the coils, because the coils are also different between two studies, can affect some of these associations or correlations, particularly within individuals. For functional connectivity density, there's an issue with thresholding. So then how thresholds can affect these findings, I think that would be another question to look at. There is also emerging evidence recently that fluctuations in the white matter, particularly, for example, during sleep, could be related to autonomic function. So kind of, I think bringing that into equation and looking at that, I think would be interesting to study, as well as also how between task and resting state these fluctuations in white matter change and their association with the rest of the brain. But altogether, this coupling between function and structure of the white matter could be an important concept and may have to be looked at also in terms of brain health. With that, I'd like to thank our team, especially my mentor, Dr. Volkov, and others who helped with various aspects of this project, and I'll be happy to take questions.